Today's video will introduce us to the ideas that will lead us into Standard 5, which covers proofs. You will need IC17 for our work today, and we're going to start by linking this idea back to Standard 4, which is all about transformations. So the first thing you need to do is think about the different types of transformations we've learned as part of that standard. So if you think through the options, the first day we learned about translations. Those were changes that caused a shape to slide to a new location. Then we had reflections, which caused a shape to flip to the opposite side of a line of reflection. After that, we did rotations, where we moved the shape counterclockwise, either 90, 180, or 270 degrees. And then our final transformation was a dilation, where the shape changed size. And so today, what we're looking at are transformations that actually cause what's called rigid motion, because rigid motion causes these things called congruent polygons to happen. And so the introduction asks us to cross out any of these transformations that cause our shape to change size. That doesn't happen in a translation, a reflection, or a rotation, but it does happen in a dilation. And so these three transformations that we've studied are going to be examples of what we call rigid motion. And the reason for that is because they are transformations that preserve the length of segments, or the other way you can think about that is the distance between points, and they also preserve angle measure. And so when a shape has a translation, a reflection, or a rotation done, the lengths and the distances, as well as the angles, won't change at all, which then forces this idea of congruent figures to happen. Congruent, remember, is the symbol where there's an equal sign with that squiggle above it. And those congruent figures are exactly the result of these rigid motions. So what happens is that when a translation, a reflection, or a rotation occurs, the figures, the pre-image and the image figures, have the same size, they're still the same shape, they have the same length in terms of sides, and then they have the same measure in terms of angles. And so they end up being identical copies of one another. If we look at this first apply section, we can see that happening. We have a shape, triangle ABC, and we're being told that it's congruent to triangle HGF. But even if we hadn't been told that, we would be able to conclude that if we were able to come up with a rigid motion or a combination of rigid motions that take triangle ABC and map it onto triangle HGF. So if I'm looking at these two triangles, it doesn't seem like a translation because this triangle isn't oriented in the same way as this one. It doesn't seem like a rotation, but it does seem like there's a reflection happening. If I imagine a line of reflection right here, then what's happening on the right side of that line is just a mirror image of what's happening on the left side. And so we can say that a reflection over, this would be an x equal line because it's going through the x-axis, and it's equal to -1 specifically, since that's the place where it intersects that x-axis, maps triangle ABC onto triangle HGF. So because of that, we know a whole bunch of things. These triangles are the same size and shape, and so what they're going to have are a whole bunch of side lengths and angle measures that are identical. They don't change. There's going to be what we call in a minute corresponding congruent parts, and we'll dig into that phrase and what it means. So our key idea, if we're talking about rigid motion and trying to get to the idea of congruent polygons, is that one of the options is for us to describe that transformation, but specifically that transformation needs to be a rigid motion. If we're able to describe a rigid motion that takes one shape onto the other, then that means that our polygons are congruent. But an alternative, especially if we don't have graphs available to us, are going to be to show that all of our pairs of corresponding parts have equal measures. And so in this triangle, that would look like measuring angle B and showing that it matches angle G. Coming back and measuring angle A and showing that it matches angle H. Coming in again and measuring angle C, showing that it matches angle F. And then also measuring the segments to show all of these segments have a corresponding match as well. Now that's a lot to have to look for, but if we're not able to describe a transformation that takes one shape to the other, then that's our workaround. We can also look for all of those matching corresponding parts and having equal measures. So digging into this idea of corresponding parts a little bit, because that's going to be where our standard 5 takes us. Those would be a description of pre-image image pairs of either sides or angles which are congruent to one another. So rather than writing out that word congruent, I'm just going to put the symbol. If you don't think that you'll remember what that means, then you might want to keep writing the word. And so what we can do is we can read these corresponding parts from the congruence statements that were given. And the way that that works is by matching up letters. And so we were able to come up with a conclusion that showed us these two triangles were congruent based on a rigid motion reflection over the line x equals -1, even though we had already been told. This one right here that they started us out with is actually a congruence statement. And so what we're doing with those congruence statements is we're showing all of our corresponding parts. A corresponds to H, B corresponds to G, and C corresponds to F because of the order that the letters have been written in. So what we're going to do in this example is look at actually a four-sided shape. ABCD would have 4 sides because there's 4 vertices, and it is being claimed to be congruent to WXYZ. We can't see the picture, so we have no idea what it looks like, but we can tell from matching up letters that angle A would have to be the same size and shape as angle W, because those are both in the first spot. B would have to be the same size and shape as angle X. We just keep right on going. Angle C would have to be the same size and shape as angle Y. And then last, angle D would have to be the same size and shape as angle Z. And so we're able to write that there are 4 sets of corresponding congruent angles because there are 4 sides or 4 corners in each of these quadrilateral shapes. If we were doing this for triangles, like the example up here, there would be 3 sets of corresponding congruent angles because there would be 3 in those triangular figures. We can also list out sides, but sides have to have a starting and an ending point because they're truly segments. So if I take 2 letters at a time now and talk about side or segment AB, that's the first 2 letters. That would correspond with side or segment WX. Sliding 1 down the line, B would also be connected to C to make segment BC, and that would be the second and the third letter, which corresponds to segment XY. C would also be connected to the next point D for segment CD. That's the third and fourth letter, so that would be congruent to segment YZ. And then we kind of run out of options because we've made it all the way through our 2 polygon names. And so if we think about what's happening, this triangle picture might help us out. AB was one side, BC was a second side, but then to close up that shape, we really connected that last C with the first letter A. So we're going to do the same thing here. We're going to connect that last letter D back to the first letter A for segment DA, which would then do the same thing over here. Last letter Z connects back up with that first letter W for the fourth and final side pair. So these congruent statements give us a lot of information about what angles correspond to what angles, thinking about the corners of the shapes, and then what sides correspond to what sides. One more piece of information here, and this is more just kind of a recap of something that we've already talked about, but we want to be 100% sure that everybody's on the same board. When we talk measurement, that's the actual size of the object. And so we always use equal signs when we're talking about that, because we're really talking about something that's a number. And so when we're talking about segment length, we symbolize that with the two letters for the start and end of the segment, but we don't put that bar above. So when measurement is involved, AB might be equal to 6 centimeters, an actual value. Or if we looked back up here at our corresponding sides, the distance between A and B would be equal to the distance between W and X, according to those corresponding parts in that congruent statement. But what we would be talking about there is the actual size of the object. If we're talking about the actual object itself, then we switch over and we use congruent symbols. And so for segments, that's exactly what I did here. I'm writing the start and end point for the segment, but then I'm putting a bar above that to show that I'm actually talking about the picture, the object itself, not just the size of the object. And so there wouldn't be any numbers involved when I'm using a congruent symbol. There would just be the names of the figures that have the same size and the same shape, just like I did in these lists of corresponding sides. When we're talking about angle measure, if you think back to standard 2, we always had that little M that showed up in front of the name of the angle. That's talking about the actual rotation value. So how many degrees the angle might be equal to. So you might write down something like the measure of angle A equals 42 degrees, an actual number. Or, as the case would be up here, if we were talking about measurements, we could say the measure of angle A is the same or equal to the measure of angle W, since those are our corresponding angles based on the order of the letters in the congruent statement. If we want to talk about the actual picture itself, the actual object, we drop the M off, and then we know we're thinking about this angle where A is the vertex, the place where the two rays have a common endpoint. And so in that case, we would never have a number involved in our congruent statement. We would just always have another angle to show that we're the same size and the same shape as another feature somewhere else, again, based on the corresponding parts in that congruent statement. All right, go ahead and flip your notes over and meet me back here for the back side. There is one more important thing for us to just formalize together. Again, this is something that we've been talking about as we've been working, but we just want to be 100% sure that we understand this before we move into the idea of proof. So just so that everybody for sure is on the same page, when we're studying geometry, remember, drawings are not often or always, however you want to phrase that, done to scale. And so what this means is we don't look at a picture and assume what's true based on how it looks. There are two ways that this might show up that could seem a little bit tricky. So objects may be congruent to one another. They may be the same size and the same shape when they do not look like it. And so what you need to do is you need to make sure that you trust labeled measures, so the actual size if it's given to you, as well as congruent tick marks. So those little dashes on segments or those little arcs in the corner of angles. It doesn't look in this little drawing that I just made like these two segments match, but if this segment has a tick mark on it that matches that one, even though this one looks longer than that one does, we believe that they're congruent because that's what those geometric markings are showing us. On the flip side of that, objects may actually be congruent. So they may be congruent when they don't look like they are. They might not be congruent, or they might be. We just don't know based on the way that the picture looks. So if I have a picture on the flip side where it looks like two segments match, those look like they're the same size, if the tick marks aren't there, I can't say they're congruent. I can't assume. All right, so from this point on, we're never going to measure to find out. So we're not going to measure angles with protractors. We're not going to measure lengths with rulers, unless we're told to, but I don't think you will be. So instead, what you're going to rely on is information that you know for sure is true. And the way that you'll know it's true is because you'll see it labeled. You'll see it with a congruent tick mark of some kind, or there'll be information given to you in vocabulary form, like they'll say there's a midpoint or an angle bisector, and you'll understand the definition, which tells you things match. Or there'll be something related to a theorem that we learn, like vertical angles theorem. We know things are congruent when they're vertical angles because of what that theorem tells us. All right.